This is chapter 19, confidence intervals for proportions. I'm going to do some examples from your textbook. So this first example deals with conclusions. How do you make a correct inclusion, and then recognizing conclusions that are incorrect when describing a confidence interval. So it says in January 2002, two students made worldwide headlines by spinning a Belgian euro 250 times and getting 140 heads. That's 56%. That makes the 90% confidence interval 51% to 61%. What does this mean? Are these conclusions correct? Explain. So the first thing I would do, so they give us 5 different choices, and we're going to decide if they're true or false. So I would start by thinking about the correct way to do this, like we talked about in class. So I would say, I am 90% confident that the true proportion of heads when spinning a Belgian euro is between 51% and 61%. I usually like to write them as proportions, 0.51, 0.61, but this is fine. So this is how we would interpret a confidence interval that, like we talked about in class. So if we look at their choices, the first one says between 51% and 61% of all euros are unfair. This is false, and one of the reasons it is false is because there is no statement of confidence. We are 90% confident. This sounds like we're 100% confident. So we have to make sure our confidence level is mentioned in our interpretation. So the next one says we are 90% sure that in this experiment, this euro landed heads on between 51% and 61% of the spins. Notice the words "in this experiment." We're talking about the population. We are making an inference about the population. We're 100% sure that the euro landed on heads between 51% and 61%. As a matter of fact, we know exactly what it was. In this experiment, they got heads 56% of the time. So this is not about the population, it's about the sample, which makes that false. The next one says we are 90% sure that spun euros will land heads between 51% and 61% of the time. Now this one kind of sounds a little better, but we're talking about the proportion of heads. And so our statement needs to be about the proportion of heads and not about the spins. And the same thing is, so that one's false. And the next one, if you spin a euro many times, you can be 90% sure of getting between 51% and 61% heads. This is also false, again, because we're not talking about the proportion of heads. We're 90% confident about the true proportion of heads. The other thing too is parts C and D almost make it sound like there's something special about that 51 to 61%. Remember, if you did a new sample, or if we did a new experiment, we'd come up with a new p-hat value, and so then we'd come up with a new confidence interval when we built that. And then the last one says 90% of all spun euros will land heads between 51% and 61% of the time. And again, this one's not about the percent of euros, but it should be about the proportion of heads. So this one also is false. So what I would recommend you do is write it correctly. And if it doesn't sound like it, then it's not right. So this is the way you want to do a confidence interval. Okay, this next problem, dealing with confidence intervals, several factors are involved in the creation of confidence interval. Among them are the sample size, the level of confidence, and the margin of error. And then we have to go through and identify which statements are true. So the first thing I want to do is remind you of the parts of our confidence interval. So when you build a confidence interval, you have your statistic, plus or minus, your critical value, times your standard error of the statistic. And this is on your yellow sheet. You might want to locate that. Okay, so for our particular confidence interval for proportions, we would have p hat plus or minus, the critical value is the z star value. Remember, I showed you how to find that on the table. And then times your standard error, and the standard error, which you can also find on the second page of your formula sheet, we get the square root of p hat, oh, there's a hat there, 1 minus p hat over n. So that's our confidence interval. Now notice they don't tell us any numbers, so we just have to come up with some statements that are true based on this information. So for the first one, it says, for a given sample size, so that means n is going to be set, reducing the margin of error. And the margin of error is this part right here. This is called the margin of error. So it's made up of the product of those two things. So we have, for a given sample size, so if we set in a given sample size, reducing the margin of error will mean lower confidence. Okay, so if we have a set sample size and we reduce the margin of error, so if we make this whole portion smaller, does that mean that we've made it a lower confidence? Well, just from looking at the formula, that's going to be true, because if p hat is going to be whatever it is from our sample, and if we are not changing n, well, the only way then to lower the margin of error would be to lower the critical value, which means that you are lowering your confidence. So this one is true. For part B says, for a certain confidence level, so this time if you're going to hold this to be the same, the confidence level, so we're not changing z star, you can get a smaller margin of error by selecting a bigger sample. So that's saying make n larger. Well, if n is larger, then that means this fraction is going to be smaller, which means if I don't change this, then I'm going to get a smaller margin of error. So this one also true. Part C says for a fixed margin of error. Okay, so that means I am setting this margin of error. I'm fixing it to be constant. I'm not going to change it. Smaller samples will mean lower confidence. So if I want to keep this margin of error the same, then if I make this smaller, then that means I have to hold on just a second. Okay. If I may have a smaller sample, then I'm making the denominator of my fraction smaller. If I make the denominator smaller, I'm making the fraction as a whole larger. Well, if this gets bigger, but the product has to stay the same, then this has to get smaller. So my z star is going to get smaller, and I'm going to have less confidence. So that is also true. The last one says for a given confidence level, so that means z star is going to be whatever it is, because the confidence level determines my critical value. So for a given confidence level, a sample 9 times as large, so if n is 9 times bigger than what it was before, will make a margin of error 1/3 as big. And that's true because you're taking the square root of 9, which is 3, so then the margin of error will be 1/3 of the size because we're holding the z star value to be consistent. So this one, also true. So all of those are true. So that's how those things are related. So it's important to know sometimes you want to have a smaller margin of error. You want your confidence interval to be consistent. You want to be fairly confident, well, there I'm using the word confident, about your estimate. So in order to do that, you have to sometimes think about those relationships and how you can balance them out. This one just gives you some computer output, and that's one of the things you want to get used to, because sometimes on the AP exam, they'll give you computer output and you have to just interpret what it means. So this says, what fraction of cars are made in Japan? The computer output below summarizes the results of a random sample of 50 autos. Explain carefully what it tells you. So how would you interpret that? I am 90% confident that the true proportion of cars made in Japan is between 0.2994 and 0.4698. So I usually go 4 places. So that's how you would interpret the confidence interval. Now remember, and we talked about this, and that's not really what this question is asking, but if you're asked, what does 90% confidence mean? 90% confidence means that if I took numerous samples of random samples of 50 cars, if I did that over and over and repeated sampling, then 90% of the confidence intervals that I would create would capture the true proportion of cars made in Japan. So that's the idea of what does it mean to say you have 90% confidence. So every time you take a sample, you get a new p-hat value, which means you build a new confidence interval. So that's a different question that might come up sometime here. All right, so this next problem, direct mail advertisers send solicitations to thousands of potential customers in the hope that some will buy the company's product. The response rate is usually quite low. Suppose a company wants to test the response to a new flyer and sends it to 1,000 people randomly selected from their mailing list of over 200,000 people. They get orders from 123 of the recipients and were asked to create a 90% confidence interval for the percentage of people the company contacts who may buy something. Well, the first thing we have to do is check our conditions and make sure that we can do this. So one of them, remember, is the idea of randomization. So we are told that they randomly selected 1,000 people. And since they're random, it's reasonable to think they're independent. Our sample needs to be large enough. So we are looking at n times p hat needs to be greater than or equal to 10. Now this represents our number of successes. So it's actually 123 because we have 123 successes. So that is greater than or equal to 10. And then we need to check n times 1 minus p, making sure that's greater than or equal to 10. This is our failure. So out of the 1,000 people, 123 place an order. That means that we have 877 that don't, but it's still greater than or equal to 10. So we're good on that. And we need to make sure that the sample's large enough, but not too large. So we have 1,000 recipients is less than 10% of the list of over 200,000. So the conditions are met. So that means we can go ahead and proceed. So when we, one of the things you want to do is name your test, or name your interval, because what's going to happen is we're going to be adding to this first thing that we're learning about. So you want to get in the habit of naming it. So we're going to use what's called a one proportion z interval, because remember we have that z star, so we're using a z interval for this problem. So we're going to build this. Remember, it's p hat plus or minus z star times the square root of p hat times 1 minus p hat over n. So that's our confidence interval we're going to build. Our p hat value, we had 123 out of 1,000 plus or minus the z star. We are doing a 90% confidence interval. I don't have the sheet to show you right here, but if you look it up, remember where I showed you to find it. So the 90% confidence level was 1.645 was the z star value times the square root of 123 over 1,000 times 877 over 1,000. I could have made these decimals. That would have been a little easier. Over 1,000. And then you can actually do this on your calculator. I'm not going, well, yes, maybe I will grab my calculator. Okay, so I did type it in. I did the -1 right here. And okay, it just went away. All right, so we see we have 0.1059. And if you were to retype this in and with a plus sign instead, you're going to get 0.1401. So that's how you write a confidence interval. So you would just go through and put that in parentheses and separate it with a comma. So that's your confidence interval. Now, I do want to show you how you can do this on your calculator. Even though you should know the formula, you should know how to build it, but if you go second distribution and, except that's not right, go stat, test, and you're going to scroll down till you find we're doing a z interval. We're using our statistics. Oh, that's not right. Hold on, let me make sure I find the right one. Sorry about that. That was for means. I need the 1 proportion z interval. So there is one that actually says that. So I just needed to keep scrolling. And then I need to type in my value of x, which was 123, and my value of n, which is 1,000, and my level of confidence, which was 90%, and calculate. And there it is. And you'll see the numbers match. But you need to be able to identify either by the name or the formula, but you are allowed to use your calculator on the AP exam as long as you name it by test, but I do want you to practice some by using the formula. Okay, on part B, explain what this interval means. I am 90% confident that the true proportion of orders the company gets from mass mailings is between 0.1059 and 0.1401. Part C says explain what 90% confidence means. In repeated sampling of size 1,000, because that was our sample size, 90% of the intervals created will capture the true proportion of, and I'm not going to write it all out again, context. The true proportion of the orders the company will get from the mass mailing. So always you want to have context when you're interpreting confidence intervals. And on this last one, I'm going to just talk about it. The company must decide whether to now do a mass mailing. The mailing won't be cost effective unless it produces at least a 5% return. What does your confidence interval suggest? And then explain. Well, when you look at the confidence interval, this is over 10% up to 14%. So my entire confidence interval is far above the 5% cutoff. So that would indicate that the company should do the mass mailing because it appears that they would be able to have at least a 5% return. All right, this last one. A National Health Organization warns that 30% of middle school students nationwide have been drunk. Concerned, a local health agency randomly and anonymously surveys 110 of the 1,212 middle school students in the city. Only 21 of them report having been drunk. What proportion of the sample reported having been drunk? So there were 21 people, so this is going to be our p-hat value. There were 21 students out of the 110 that were surveyed. So that is about 0.191. So that is roughly 19.1% reported having been drunk. All right, so then part B says, does that mean, or does this mean that the city's youth are not drinking as much as the national data would indicate? Explain. We can't really say that because this is from one sample. And we know that if we take another sample, we're going to have sampling variability. We're going to get different proportions. So we need a confidence interval. All right, so in order to do a confidence interval, we have to make sure that we can. So we have to check conditions. Sorry, but you're going to have to get used to this. So the first thing is the randomization. So we should be able to say, if I could spell randomization, there we go. So in that one, we are told that they randomly and anonymously surveyed. So we are told that it was a random survey. So we're good on that. Because it's random, should be independent. So the students should be independent of each other because they did this randomly. Our 10% condition, I guess I usually do the other one first, but the 10% condition, we know that 110 students is less than 10% of 1,212. And then we also need our success failure condition, that the big enough sample. So n times p hat in this case is our successes, which is 21, which is greater than or equal to 10. And n times 1 minus p hat would be the people, would be the other ones. There were 89, also greater than or equal to 10. I know I'm saying successes are the ones that said they had reported being drunk, but that we were looking to find that. Remember, I've said success doesn't mean it's a good thing. So the conditions are met, so we're going to use a 1. My test is, or my procedure is going to be a 1 proportion z interval. So when you build this, we're going to have, remember the formula, p hat plus or minus z star times the square root of p hat times 1 minus p hat over n. The more you write it, the more you'll get used to it. Now you can write the formula. You could plug the values in, but if you wanted to instead go to your calculator, we're going to do stat, tests, and we are dealing with our, I did it again, didn't I? We're going to go stat, tests, And I'm going to go find, I went up instead of down because I think it might be closer. There's a 2 proportion z interval, but we want the 1 proportion z interval. So it's right here. And we have, it remembered what I had in before. So we have 21 out of 110. And we want a, what did it say? 95% confidence interval. And then calculate. And we get our answer. So we have 0.1174 or 75, if I round that right, and 0.2644. Okay, so that's my confidence, or my confidence interval that I get. So now it says to create it, and we did that. Is there any reason to believe that the national level of 30% is not true of the middle school students in this city? Now, remember how we interpret this. I am 90% 95%. So I am 95% confident that the true proportion of middle school students in this city, the true proportion of middle school students in this city who have been drunk is between 0.1175 and 0.2644. Now, I haven't answered the question yet, since 0.30 is not in the interval, I have evidence to suggest the proportion for this city is lower. Do you remember when I told you that this is not a math class and that this is really more of an English class and communications? We're to that part now where that becomes obvious, because you will find that you are writing a lot in your explanations, and that's what you have to do. So I know this was a little bit long, sorry about that, but there's just a lot of details we have to remember for confidence intervals and how to interpret them correctly. So there you have it.